So, welcome again to the new lecture of the course Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap what we were doing in the last class. So, in the last lecture we were talking about, we finished our discussion on phase diagrams of PZT, for example, which is a solid solution of PbZrO3 and PbTiO3. Both are perovskite structured compounds and they make extended solid solution. And the important thing about this phase diagram is that it contains a morphotropic phase boundary at 4753 or nearly 50-50 composition, at which both rhombohedral and tetragonal phases coexist. As a result of coexistence of two phases, the dielectric constant is very high as well as the polarization is very high, and this is the, so near 50-50 compositions are most useful compositions of PZT, and this is by far the most successful piezoelectric for various applications. And then we were looking at the details of ferroelectric measurements. How do we make ferroelectric measurements? We saw that the ferroelectric measurements are made using something called a Sayer-Tauber circuit, and the important thing is to make these measurements in such a manner so that you do not consider artifacts as a real ferroelectric. So, a good ferroelectric loop would be something like this, or something like this. But if you have a ferroelectric loop like this, for example, so these are good ones, okay, these are good ones. But if you have something like this, let us say, then this is a bad ferroelectric loop. If you have something like this is a bad ferroelectric loop. So, when you get these bad ferroelectric loops, then you must make measurements at different temperatures to see what is the intrinsic contribution, because if you have a rounded loop generally, so basically you can say the rounded loops without saturation have higher electrical leakage, which means sample is of poor quality, it contains defects, it contains entities which give rise to high leakage. As a result, often one needs to low temperature measurements to distinguish between the ferroelectric contribution and the leakage contributions. Even at low temperatures, there is a possibility that you may not get saturated loops. So, you must be aware of what is good and what is bad, and do not report the bad loops as a ferroelectric loop. So, now let us go to the details of this lecture. So, here so we would like to, so we have seen ferroelectric measurements. Now, next we move on to how do we make piezoelectric measurements. Now, piezoelectric measurements are basically based on measurement of direct or indirect piezoelectric coefficient, right. So, so you can see that direct piezoelectric coefficient is, and the most common of them is to D33, measure D33, okay. So, D33 is nothing but, you can say, so direct piezoelectric coefficient is when you apply stress, you measure the polarization. So, basically you are measuring Coulomb versus per Newton of force, that is what is direct piezoelectric coefficient. So, basically the polarization is the response and force is the this is the applied force. So, this is what is direct piezoelectric coefficient, and indirect piezoelectric coefficient would be so let us say indirect would be D33 prime, let us say it would be the when you apply electric field you are measuring the strain. So, that is basically you can say strain divided by volt per meter. So, basically what you are measuring is meter per volt. Okay. So, how much is the change in length that you observe or change in height that you observe upon application of a certain voltage. So, this is what is the indirect coefficient, and there are various methods which achieve this. So, in piezoelectric case there are direct techniques, such as direct techniques also you can have two of them. So, you can have piezoelectric effect and you can have indirect piezoelectric effect. Okay. So, among these also we have lot of techniques. We have just the technique based on the application of normal load. So, basically what you do is that you have a sample which is, so this is your sample is sandwiched between two electrodes and then you apply a mechanical load and then you measure the basically for a force. If you apply a force F, and you basically measure the electrical charge. Or dielectric displacement as we say, right. Okay. So, basically D33 effective in this case would be del of, let us say D, let us say in this case D3 to del of sigma 3, okay, or F3 you can say. So, this is what you are going to measure, and this is nothing but Q divided by F. Okay. So, this is what we measure in this case. This is a very simple method, but the problem here is the tips, when you apply force using a tip, the tip has to be in contact, and also how the so generally what happens is that in these samples the tip is so this is, for example, we do it in piezo force microscopy. Generally the tip is not flat and tip tends to be, so if you have a sample the tip tends to be like this. So, there is a problem in calculating the effective area which is of contact, and secondly the electric field distribution within the sample that is rather uncertain. So, this is a easy technique to measure the piezoelectric effect, and the second method that is used is what we call as periodic compressional force, use of, so this is first, and the second one would be use of periodic compression force. In this case what happens is that there is a piezoelectric transducer. So, this is a piezoelectric transducer which is in contact with the metallic rod. So, this is a metal rod and this rod is then in contact with, so on the bottom we have a silicon, we have a substrate, let us say a silicon. On the silicon we have metal and then we have a piezoelectric. So, this is piezo, and then in between we have what we call as a coupling liquid. So, using the piezoelectric the vibrations are transferred using from the top metal to the piezoelectric, and that is how you measure the charge. Now, this uses a coupling liquid to ensure that the charges which are generated are over the uniform area and the force distribution is small, and then you also compare this with a reference. So, you use a reference sample to make measurement, so that you compare the charge generated in the normal sample with respect to the reference sample. So, this is a good method, but it is not very easy to make, because you can see that use of liquid and stuff like that which makes it complicated. And so, this is second method, and the third method among this is called as cantilever method. This is the most common method. So, in the cantilever method you have a cantilever which is pushed against a pointed, let us say there is a cantilever which is moved up or down, and this cantilever pushes the, so this is sort of a strained beam kind of, you can say, it's kind of a cantilever. This is, let us say, the cantilever, and this is the beam on which your sample is coated, let us say, okay. And then this is connected to your what you can say, and there is a load somewhere here, and then this is connected to a oscilloscope, okay. And you measure the basically displacement of the, by moving this cantilever up and down, you measure the displacement. So this is a very easy method, but the but again the problem is the strain produced may not be uniform, and there could be a problem with different kinds of samples. So you have to use a silicon cantilever on which you have to coat the film. So when you coat the film is of certain quality, but when you make a real sample, the real sample quality may be different as compared to what is coated on the beam. So those are the issues that may be there. There are other methods which are also, there is a pneumatic pressure rig measurement, and there is also what we call as optical interferometry. So optical interferometry is a popular method nowadays for measuring the piezoelectric coefficient. What happens in this case is, in case of optical interferometry, is you have a laser, and this laser goes through the lenses, okay, and then it goes through a beam splitter. Let's say this is the beam splitter, and then this laser falls on a sample, okay, and then using the beam splitter, the laser also goes through the lens to a photodiode. So here we have a photodiode, okay, this is lens, this is also lens, and then this photodiode is connected to what we call as a to a feedback system, okay, and then this laser through a beam splitter is connected to a reference mirror. So we have a mirror, and then here we have a transducer, and when the laser falls on the sample under a load, it generates a signal. This signal goes to lock-in amplifier. So we have a lock-in here, and this lock-in is connected to some recording device, okay, and then this photodiode takes signal from lock-in, and then this goes to the monitor, okay, or oscilloscope or whatever it can be. So basically you are measuring the oscillations on the surface of the sample using a laser beam here, and you are comparing that with a reference sample, and that is how you make the measurement of this is a technique which is used in nowadays in a few commercial samples, especially for thin film measurement, because direct measurements are not easy to make on thin film samples. They are more suitable for bulk sample or thick samples, whereas for thin films, very thin film, the optical interferometry method is more popular. So these are certain methods for making the measurements of direct type, and then we can have measurements related to surface acoustic waves, or bulk acoustic waves. These are typically the indirect methods, okay. So they are basically coupling of acoustic waves with respect to sample, which are used to measure the piezo response. So in case of single beam, in case of optical interferometry, the resolution can be quite high. So we can measure up to about 0.1 picocoulomb per Newton. So this is a fairly high resolution, and the displacements that can be measured of the order of 10 to the minus 3 nanometer range of displacement. So very accurate method. If you, on the other hand, if you look for cantilever method can measure up to about 0.6 coulombs per meter square resolution. It has pretty high sensitivity, 0.6 coulombs per meter square is pretty high sensitivity. You can convert this into microcoulombs per centimeter square, and that tells you that this is quite sensitive method, and it's also direct, so it's very useful method. And then if you look at the application normal load, this has a lower accuracy. This has an accuracy of about 20 picocoulomb per Newton, okay, plus minus 20 picocoulomb per Newton. And the periodic force, the periodic compression is about 0.03 picocoulomb per Newton accuracy. Pretty accurate, but a little difficult measurement to make because of use of liquid and things like that. So among direct methods, the popular methods are application normal load and cantilever method and the optical interferometry method, whereas among the indirect methods, surface acoustic waves or bulk acoustic wave type of methods are more important, basically based on resonance and so on and so forth. Now let us look at the piezoelectric measurements. Sorry, not piezoelectric, pyroelectric measurements. So in case of pyroelectric measurements, what we are measuring here is basically there are again two methods. One is, the first method is called as static method. In the static method, what you are doing is that you are measuring the hysteresis loop as a function of temperature. So let us say you measure hysteresis loop at one temperature, then you measure hysteresis loop at another temperature, and so on and so forth. So basically you make temperature dependent PE measurements, and then from this you can plot what is the, this can lead to what is the plot of polarization as a function of temperature. So you will have a plot something like this, okay, for a second order phase transition, and then for a the change in polarization, let us say if you zoom this section, then you can, so this is P versus T. From this we can determine what is small ps, which is small pi, which is del ps by del t. The slope can give you from the linear region the change in the pyroelectric coefficient. But the problem is that it is in this case it is not suitable for materials with higher coercive field. So which could be higher than their breakdown field. So if the coercive field is very high, especially if it is more than the breakdown field, then it's not then it leads to conducting samples, and it's not a very useful measurements. Another measurements, this is called as dynamic method. This dynamic method is basically measurement of you can say the pyroelectric current. So when you have this varying spontaneous polarization as a function of temperature, this varying spontaneous polarization causes a change in the current, which is the pyroelectric current, and you measure this current basically. So what you have here is this current is basically, you can say, into, so if you look at this is polarization, which is microcoulomb per cent. This is the pyroelectric coefficient, this is temperature, and you have to multiply by the time. So Q is equal to IT, right. So I is equal to Q divided by T, and from this you can measure what is the pyroelectric coefficient, which is I divided by A, the area of the sample, into the change in temperature as a function of time. So you are measuring current as a function of change in temperature with respect to time. And basically this is a very simple circuit. What you have here is you have a you have a sample here which is, let us say, the sample will have certain resistance, and as a result you have certain current passing through the sample. This is basically, it is kept in an oven which is or a furnace with a controlled scan rate, and then you have a, basically you can say, on this side you have a voltmeter, and you measure the current which is flowing in this direction. So, taking through a voltmeter you measure the current, right. And so if you have a circuit like this, let us say the resistance of the circuit sample is, let us say, RC, and then resistance of the measuring circuit is Rm, then we can say Im will be equal to I into Rc divided by Rc plus Rm, where Rc is the sample leakage resistance basically, okay, and Rm is the, you can say, device resistance, right. Okay. So, you can see that Im into Rc plus Rm is equal to I into Rc, that is what you are interested in measuring. So, this is a simple measurement for so measurement of pyroelectric current is the simple way of measuring the pyroelectric coefficients. And then of course, there are other methods such as laser intensity modulation methods and so on and so forth, which you can get into details. Now, what we would like to do that is we have discussed the ferroelectric, the physics of ferroelectric materials, the pyroelectric materials, the piezoelectric materials, the mathematical expressions, the phase transitions, the kind of crystal structures they have. So, about the now let us look at certain applications of these materials. So, you can say first we will look at the application of piezo electric materials. So, let us see some of the piezoelectric materials, the applications. So, the first application let us consider that is of a gas lighter, which is a very simple application, just to light the gas by generating a current in the circuit. So, let us say, what does this require for this LIGHTER? So, what does this require? You need two piezoelectric pieces. Okay. So, let us say A and B, these are two piezoelectric samples. We take it in such a manner so that their polarizations are reversed. So, let us say one is this polarization, another is this polarization. So, two pieces with opposite p direction. Okay. So, when you take these two samples, let us say in this sample you have up and another sample you have down, and then when you apply the stress, so then you apply the stress to them. So, let us say you apply stress to this, stress is, let us say, in this fashion. So, then you say you apply stress to both pieces. So, when you apply stress to both pieces, so you will develop the polarization, right. So, let us say one of the samples has charges like these and another sample will have charges like right. When you apply stresses, the polarization will increase. So, you can say polarization will increase. And what will polarization increase mean? Polarization increase will mean that you have increase in the surface charge density. So, your surface charge density increases, and then what you do is that you bring them together. So, now you can say, sorry, bring them together. How do you bring them together? You bring them together because the same charges will come together. So, basically when you bring the same charges together like this, then these charges, let us say here, this will generate a spark. When they are pressed together, they will generate a charge, and this will basically lead to, so you will have a circuit connected, and let us say this is the circuit which is the positive charge. From here you will flow the negative charge. So, this is the negative charge, and hence this will generate the spark. So, this will across the gap, when the charges combine together, it will generate the, so this is where we will have spark generation when you bring them together. So, basically you take two pieces of opposite polarization, apply stress, create more polarization, bring the same charge faces, same sign of bring the opposite faces together, so that the positive faces are in front of each other, or negative faces are in front of each other. So, positive charges will flow to one direction, negative charges are taken through the outer circuit, and then the positive and negative meet with each other, they will create a what we call as a spark. Okay. So, this is what this gas lighter is going to work like. Now, there are other applications as well. Piezoelectric is a very useful material. It is used for other applications such as if you know that ultrasound measurements, right. Ultrasound testing, it works as a transducer, it works as a actuator, and so ultrasound testing is basically on the principle of detection of ultrasound waves which are generated using a piezoelectric. So, they are very useful for medical applications. Transducers are the ones where you create a transduction. Transduction means create a linear motion. So, wherever you want to create a linear motion, you can use the piezoelectric. Actuation means you provide actuation, and then you can again, it is a motion related device, you can create an actuating device. So, we will look at some of those applications in the next class. Okay. So, what we have discussed in this class is basically the principles of measurements of piezoelectric and pyroelectric measurements in very brief manner, and now we are going to and then we looked at the applications of piezoelectrics. We will continue on the application of piezoelectrics and pyroelectrics as well as ferroelectrics in the next lecture. Thank you.